I recently purchased another addition for my bench, a Heathkit PS-4 high voltage power supply. It's now time for its restoration, and I thought you might want to come along for the ride. I'm Steve. Welcome to my lab. Here it is, simplicity at its finest. Heathkit manufactured this model between the fall of 1958 until it was replaced by the cosmetically updated model IP-32 sometime in 1962. This circuit design was a significant improvement over the previous model PS-3 power supply. Interestingly, that circuit design remained relatively unchanged over the next 4 variants of this power supply, lasting until 1982. Let's take a closer look at it. Before we go too far, let's take a look at the overall exterior condition of this power supply, which I think is mint. I can't believe how clean this is. Now, I haven't done anything to clean this thing up. This is the way I received it, and boy, it's a beauty. A couple of scratches on the front panel here, not a big deal. I think there's some fingerprints and some smudge marks lower, in this area. The silk screen is perfect. The meters have a little bit of yellowing, not too bad. Obviously there's a little bit of dust on here, but I think this thing is, overall the front panel is like in excellent shape. I might be able just to polish this thing up, polish the plastic on these meters, and this thing will look like the day it was first pulled out of its shipping box. Very, very nice. Now, the person that sold me this power supply said that there was a problem with the voltmeter reading correctly. Again, I haven't powered this thing up, so I don't know what the story is, where this meter doesn't necessarily read the right voltage. Wasn't clear whether it had the same problem on the C- and the B+ supply, or what the story was. We'll give that a check out. Hopefully we don't have a big problem with the meter, because I have no clue where I'm going to get one to replace it. But we'll worry about that when we get there. So continuing to look at the condition of this thing, look at how clean this case is. Again, there's a couple of small dings on it. The screws that hold the case together, some of the paint is chipped. Otherwise, this thing is like immaculate. I think if I go to wash this case, I don't know how much cleaner it's going to get. This is like in very, very, very nice shape all the way around. It's very clean. I don't think I have to do much with the case anyhow. Even the handle, it's a plastic handle. There's not even any scratches on the plastic handle. So I think that's pretty nice. Now, the only thing that I'm questioning, and it's really not a question, is this power cord. I don't think this is the original power cord. Looks really nice. It's nice and pliable. Look at that, huh? Do you think that's 60 years old? Let me tell you, I'm over 60 years old, and I wish I looked half as good as this power cord does. It's a non-polarized cord, but it looks relatively new. I think this might have been changed, and maybe some other things inside. When we go inside, we'll see if some other things have changed. I haven't decided what I want to do with this power cord yet, whether I want to put a polarized cord on, or whether I want to put a grounded plug on here. I got to think about it a little bit, but I mean, I could really stick with this if I wanted to. This is nice. If I'm going to replace this cord, I'm going to throw this in my parts bin and use it someplace else. So other than that, I think I got a pretty good buy here. Hopefully it works. Check this out. Professional grade electronic test equipment from the late 50s and early 60s. No digital displays with words in obscura font. No multi-dysfunctional switches that you got to remember the order and the direction to turn things in. It's got 2 outputs, and it's got 2 knobs to control. You turn the knob, and you get the voltage. Nice and simple. let's take a look at what these knobs actually do. Over here we have a single turn pot for setting our B plus output voltage. Our B plus output voltage varies between 0 and 400 volts DC, and that will appear on these two terminals. Obviously, this thing was designed when men were still men. Where else, or where today, can you find a piece of test equipment where your finger is literally less than 2 inches away from 400 volts DC? Doesn't get any more scary than that. But anyhow, you turn this knob. This is a linear pot, so its position is pretty linear with voltage up to 400 volts DC. This supply can supply 400 volts. This thing's turning on me here. Can supply 400 volts at 100 milliamps continuously, and intermittently it can supply up to 125 milliamps. That's pretty good. Pretty good output. On this side, as the power supply turns in a little bit, this pot adjusts C minus output voltage, which appears at these two terminals. 0 to, it says minus 100. Depends on the load on these terminals, I would think. You know, looking at the schematic, we're going to talk about that in another video. But it only supplies 1 milliamp. This is for supplying voltages to control grids or, you know, very, very low demand applications. It's a nonlinear pot, or that's what it says on the schematic. So I'm imagining that, you know, if it's a logarithmic scale, you know, at 50% rotation, it's probably, you know, probably sitting in the 12 volt range or so. But again, you know, you turn the pot, and what you see is what you get. Interestingly, about the minus, the C minus output is when you're hooked up to these terminals, and you can, you know, also plug your meter in here. What you see is you'll see a negative voltage if you reference your meter, the common on your meter to the black terminal, and the positive on your meter to the red terminal. As you turn this pot clockwise, you'll see the voltage on this binding post become more negative, right? And it says minus 100 because it comes off of one of the 150 volt tubes, and the way the circuit is set up. It's probably, depending upon the load, it could go over minus 100 volts. And, you know, we'll take a look at that. We'll do some testing when we power things up, see how that works. Already, we've talked about 50% of the knobs on this thing, so it's pretty simple, right? Up here, we have a power switch. We saw that. We're going to see how that works a little bit more later on. It's a 3-position switch: off, standby, and on. And the standby position, it energizes just a filament transformer, and the filament transformer supplies the heaters in the for the circuitry of the power supply. And there's also a separate winding on the filament transformer that comes out on these two binding posts that can supply up to 6.3 volts AC at up to 4 amps for a circuit under test. And anytime I'm in standby, that filament transformer is energized. There's voltage appearing here. The heaters on the tubes are energized. Everything else is dead. I take that back. When I'm in standby, the power lamp also lights, because this power lamp, I believe, lights off of one of the windings in the filament transformer. When I turn the switch to on, it continues to power the filament transformer, but it also energizes a power transformer that supplies power to all the tubes internally. It also supplies output to the C minus output and the B plus output, right? So I can keep things warm by keeping the switch in the standby position. When I turn it to on, that's when I'll see the voltage appear here. I got 2 meters on the front panel. I have it says the DC output current. This meter is in series with the B plus positive output terminal. So any load that's on the B plus power supply, I can read the current up on this meter, and you can see that, hopefully you can see there's a little red tick mark at 100 milliamps to kind of show the normal maximum operating range, although we said intermittently we can go to 125. I can't read the current on the C minus supply. The C minus supply, again, is for very low, it is, you know, for supplying control grids on tubes, very low output. They say 1 milliamp. We're going to do some playing around to see what kind of current this C minus supply can source. It's not much, I guarantee you that. So again, the DC current output only looks at the B plus side. I have a voltmeter, and the voltmeter I can see has two scales. It has the top scale is 0 to 400. The bottom scale is 0 to 150. I have a way that I can switch the voltmeter between reading the B plus supply and the C minus supply by throwing this meter switch, appropriately named, right? Depending upon if I put it towards the B plus side, I can read the voltage that's appearing at the B plus terminals. When I move it to the left, the C minus side, I can read the voltage that's appearing at the C minus output. And again, if I'm reading C minus because it's a 0 to 100 minus 100 volts, I'd read it on the lower scale, where the 0 to 400 volt scale is for reading B plus. I'm switching in resistors that will appropriately scale the meter so that, again, 0 to 400 is the B plus side, 0 to 150 is the C minus side. We're going to see how that meter works in an upcoming video. Pretty simple, right? Only thing you got to worry about is killing yourself. But we'll talk about that later too. Here we are on the inside of this power supply. We're looking at the top side of the chassis. You can see the back side of our front panel meters. This one over here is the current meter, and this is the voltage meter output for both B plus and C minus power supplies. Our indicating light, our power switch, which is off, standby, and on. Standby is just for powering a filament transformer. On is powering the whole internals. Here's our filament transformer. This transformer has 4 separate windings in it, separate and isolated windings. 3 of them are for heaters for the internal tubes. One of them supplies, it's a dedicated winding, supplies 6.3 volts AC at 4 amps to the front panel. This is our power transformer. Now again, our power transformer is only energized when the power switch is in the on position. The filament transformer is energized anytime the power switch is either in standby or on, and the main power indicator will also come on anytime the power switch is in standby or on. All right, let's take a look at the tube complement we got here. I'm going to tilt this back a little bit so we can see it a little bit better. There's not a lot of dust in here. We don't see a lot of corrosion. It looks pretty nice, doesn't it? Wow. This thing must have been like stored in a hermetically sealed container or something. It's very clean for something that's probably over 60 years old. So the guy did a nice job of storing this thing. Before we get to the tubes, there's 2 internal adjustments over here. Pots are mounted on the bottom. Screwdriver adjust, single turn pots. I don't remember which one is which, but one of them is for setting the 0 volt output for the 400 volt power supply, and the other one is for setting the 400 volts. So I can do 0 and span on the 400 volt supply. Tube wise, I have these 2 big tubes are 6L6 GCs, obviously the GCs. Those are our series regulator tubes. They operate in parallel. This tube right here, by the way, I cheated. I looked in here before I turned the camera on, so I know what's what here. This is the control valve amplifier tube. Gets all the feedback, controls the control grids of the series regulator tubes. That's a 6BH6 tube. These 2 tubes right here are voltage regulator tubes, OA2 tubes. They're 150 volt nominal tubes. They supply various references and biases throughout the circuit, and they also supply one of these tubes. We tap off of it to supply the 0 to minus 100 volt C minus supply. This last tube right here is a 6x4 tube, and this is a dual diode tube for supplying the DC voltage for the two OA2 tubes. So again, it looks pretty clean. A little bit of rust on the end caps of these transformers. Doesn't really scare me because I don't see a lot of other corrosion or other nasty things going on here. This is going to clean up really nice. You know, a little bit of cleanup. I could probably wipe this off with my finger right now. So it's not going to take a lot. I'm not sure what I'm going to do. I might take these end caps off, clean them up, and repaint them, but we're going to see what's going to happen there. All right. So all in all, it looks pretty nice. Looking at the bottom of this chassis, this whole power supply is amazingly clean. I don't know if this was assembled by somebody. Obviously it was assembled by somebody, but as far as somebody buying the kit and assembling it, or whether it was done at the factory, but it looks like a pretty nice job. You know, everything looks like it's nicely soldered. I don't see a lot of garbage, you know, flux and other things all over the place. So, and it's very clean. Very clean. Now, I was concerned that somebody was in here because the power cord looks like it might have been changed at one point, because it's for something that's 60 years old. This power cord, you would think would be like dried twigs, but it's really not in that bad a shape. And as I look in here, I think the only thing that stands out to me as possibly being changed besides the power cord is this capacitor right here. I would think that it would have been another one of these Ashton Mini-Mite caps. I believe that's a 20 microfarad cap. But other than that, I mean, and again, they did a nice job. Doesn't look like a butcher job replacing that. Lots of, don't see any roundies in here. Doesn't look like anything's burnt up. You know, usually you might see something in here smoked or leaking. Looks like it's in pretty good shape, though. Here are the two adjustments for the zero and the span on the plus 400 volt, the B plus power supply. These potentiometers for setting the B plus. This is the B plus pot here, 0 to plus 400 volts. This is the C minus adjustment pot, 0 to minus 100. They look pretty clean. We're going to check those out, make sure they're okay. I'm going to replace all these capacitors. I've already bought new capacitors. I haven't tested any of them. I haven't powered it up yet. We're going to power it up through my dim bulb tester, a dim bulb with a dim bulb tester, and you know, we're going to see how it operates. But I'm not expecting good things for these caps. I guess we'll see. I bought all new caps in anticipation. Some interesting things we see in here. These guys right here. These are selenium rectifiers. You don't see those too often. Definitely, you could tell this power supply was designed and built in the late 50s. And if you think they look like they're wired in series, they are. Again, you know, throwback to the 50s, they probably were a little concerned about the life expectancy, reliability of these rectifiers. So by putting two of them in series, if one of them failed, it would still work properly until the second one failed, right? And because they're the same kind of rectifier, selenium rectifier, they probably have the same failure modes and probably wouldn't last too much longer. If one failed, the other one would probably be close behind, but that's a story for another day. All right? Over here, look at these guys, huh? These are part of the B plus power supply. We feed 600 volts into the series regulator tubes, our octal, 8-pin octal tubes here. We feed 600 volts. That 600 volts is rectified This is a voltage doubler circuit with these 70 microfarad caps, these two 70 microfarad caps. These are silicone diodes. Look at these bad boys. And if you look close, you can see that they're connected together, and the way they're laying in here, I guess if these things were turned around a little bit better, those clips are pretty tight. We'd see that, again, they're diodes in series. We're worried about reliability. Or somebody was worried about reliability from the 50s. So what they did was they had diodes. They always put diodes in series in case one failed. And these things are beautiful. Man, they're big. Probably going to replace these. And probably the nearest equivalent today would be like a 4007, 1N 4007 diode will probably fit in there nice. And when we see these diodes with their modern contemporary diodes, there's quite a difference in the size. Likewise, I'm going to replace these selenium diodes with just regular silicone diodes. We'll see that as we go along here. Power fuse here, nice and dangerous. If you're doing testing around here, have 120 volts hanging out. That would be easy to hit. Before we do any testing, I'm going to give that a wrap. But I mean, even this looks like it's soldered nice. Nice solder job. Probably could have been a little bit more heat on that, but that's okay. So again, whoever put this together did a pretty nice job. Let's take a look at this fuse, see if there's one in here. It feels like there is. See if I can read this bad boy. Let me pull it out from behind the camera so I can take a look at it. It says it's an AGC3, which is not what's supposed to be in there. It's supposed to be a 1.5. I have to change that before we go to power this thing up. I guess if 1.5 is good, then a 3 amp fuse is twice as good. So anyhow, it doesn't look like, I don't know why somebody would change that, but certainly doesn't look like anybody was doing some smoke testing in here, because everything looks like it's in really, really good condition. This is going to be an easy cleanup. Again, I have all new caps. I have new diodes. These resistors, I'm not really expecting a whole lot of problem with them. But I do have, in my private stock, I do have a big supply of metal film resistors. The only thing that makes me a little nervous is these guys. Some of these resistors are running, at like 50% of their rating. So they may have changed a little bit. There's not a lot in here to check, and we'll give that a test and see what we need to replace or not. But not until after we fire it up, see how it works. Hopefully, when we do that, we're not going to let any smoke out of any of these parts, but I guess we'll see when we get there. So there you go, 5-cent tour of this project. I think this is going to be a 3-video series. In the next part, we're going to power up the power supply just as it is. No repairs done on it. See how it performs. Hopefully it won't blow up. Then we're going to start the restoration. In part 3, we're going to finish up the restoration and again test it, see how it compares to its original design specs. I think it's going to be a lot of fun. I'm also thinking that someplace along the line I might do a full schematic review, make a separate video just talking about how this power supply works. I think there's a couple of other supplies, other manufacturer supplies that are very similar in operation, tube-type power supplies that are very similar in operation. So it might be interesting. Let me know what you think. If you're interested in that, put it in a comment below, or anything else you'd like to know about this power supply. Put it down in the comments, all right? Hopefully you enjoyed this, and looking forward to seeing you on the next ones. Till the next time, be safe.